is designing a BESS for data center applications. So what we're going to do is like, now there is a lot of talk about flexible data connection, data center design, adding solar plus storage to add some flexibility so that if you are having interconnection, a lot of network upgrades because of interconnections and delays to your project, you can basically try to bring your interconnection limit down and be flexible in the time of like high peak time. So the project that we have planned for this one is that we are designing a 100 megawatt data center load. The utility basically for this case, let's say that they cannot connect 100 megawatt without a lot of network upgrades. So they could allow up until 90 megawatt. So the owner here, in this case, is looking for a combination of solar plus storage to see if they can bring the overall site load down to 90 megawatt and not exceed that. So in that way, they can still get connected. And in those high power scenarios, they are going to be able to use batteries and storage. So one thing to mention is that we are not considering any kind of data center load management or algorithm shifting or time shifting of algorithms. So right now, this exercise is mostly if you want to add solar plus storage, what should the size of your storage that could allow you to decrease your interconnection limit from 100 megawatt to 90 megawatt. So we have a 90 megawatt interconnection limit, 100 megawatt of data center load, 75 megawatt of PV, and we want to determine the best capacity by running the simulation through Storlytics. So what we're going to do here is we are going to go back to the software and we are going to open an example file for this. We go under File, open example underscore data center. Once you load it, we're going to jump to the battery profile creator module. So we have talked so far, both the examples we did focused heavily on the battery system modeler. We also have this module, the profile creator, that basically allows you to size your battery systems for applications, right? So we're going to come here and we're going to select microgrid demand. So you come here and select microgrid demand. We're going to input 365 days for this exercise, time is step of 1 hour. And we're also going to select this option of copying the output profile for it to be an input to the battery system modeler. Because the output of this module is going to tell us how big of a battery we're going to need from a point of interconnect perspective. So do we need a 10 megawatt, 40 megawatt hour battery for this application, or we need a 100 megawatt, 800 megawatt hour battery, right? So what this module is going to help us answer is that, what should be the size? And then it's also going to give us a profile that, your battery is going to be operated at this way. And then we're going to take those two input, we're going to input that into this other module and complete our design. So in the first module here, once you are done with the general tab, jump to the microgrid demand. If you have selected microgrid demand here under apps, your microgrid demand tab should become enabled. First thing you load in is the load profile for the data center. So if you click the drop down, it should be already pre-populated, but if you want to bring your own profile, you can come in here and basically you can load your own profile. So right now we are using this one, data center example load profile. So that one, if we zoom in a little bit, let's see. The red one here is our data center load. And it shows that there are a handful of the time in the year that data center is crossing that 90 megawatt of threshold that we have set for interconnection. So actually, during those time, it will be good for the batteries to discharge and make sure that the data center output doesn't exceed that 90 megawatt threshold. So we loaded the data center profile. And the second thing we have to load in this case is the PV profile. So we also loaded that PV profile. If you click the drop down, you should see a data center example PV profile. Select that one. Once you select that, if you have auto update on, this figure should automatically get updated, and you should see that the PV coming is in the negative axis. So here, positive means from a battery perspective, discharge, and then from a load perspective, positive means load, and negative means generation. So here the solar comes in as negative injections. So once you have your solar profile loaded in as well as your data center profile loaded in, the black one that you see here is basically your net. So that's the net of your load and your solar. Then you go to the dispatch parameter. So this is where you basically set the logic that when the battery should react. So on the discharge side, we set a logic that the net of solar and the data center load should not cross the interconnection limits of 90 megawatt. So we set the discharge threshold to be 90 megawatt. So what does that mean? So what that means is that whenever that net demand is crossing the interconnection limit of 90 megawatt, the battery is going to be discharging to provide for that energy. And basically overall plant production or consumption is not going to go above 90 megawatt. And then on the charge side, we also have to make sure that we charging the battery. So for the battery to be able to discharge, charging the battery does not create a new peak, right? So what we do is here we set the charging threshold to be around 60 megawatt. So once we do that, what you can see here on the curve, there is a blue line, that's the discharge threshold at 90 megawatt. And then there is a green line, that is the charge threshold at 60 megawatt. So basically, whenever the net demand is going to fall below that 60 megawatt, that's when the battery is going to start to charge. That means the battery has some headroom before it reaches 90 megawatt, and your battery is not going to cause a different peak. So that's why we added the charge threshold to be 60 and the discharge threshold to be 90. So once that is done, then you go to the global input parameter, and then you utilize these two features. So first feature we are utilizing is we're also trying to apply a hard limit on the charge and discharge limit, because on the discharge side, we want it to be 100 megawatt equal to the data center load, because if there are outages and all, the battery should be able to provide the data center by its own. On the charge side, we do not want the battery to create additional peak just because it was trying to charge at a higher power. So we applied a 25 megawatt of charge limit so that in that way, your battery charging rate is slowed down, and you're making sure the battery is not causing additional peak, because one of the nature of this data center load profile, you'll see that is very like flat, right? It's more or less flat. It's up there. So there is not a lot of valley where your battery has a lot of headroom to charge. So you have to limit how much the battery can, like whatever power level the battery can charge at. Once that's done, then the next thing is that you have to apply that equalization, and that's important because a lot of times if you are just charging based on this profile, some days you can see there is just not enough energy available from the solar to charge your battery for the discharge. So to do that, to counteract that, you add this energy equalization feature. So you're basically setting a time window between 7 a.m. to 5 p.m. That basically tells that in that 7 a.m. to 5 p.m., whatever amount of energy you needed to discharge in that day, you're making sure that you're putting enough amount of charge energy back into the battery, right? Because otherwise, if your battery doesn't have energy, it's not going to be able to give any energy. So you're setting a time window, and you're setting a charge-discharge ratio, and that's basically controlling how much energy you're putting in. So if from your solar, if you're not putting in enough, then during this time period, you're going to take help from the grid and put some additional energy so that your battery has enough energy. Done, you go ahead and run it. And then look at the generate report. And one feature I'll show you as well as the report gets generated is that now, even without running it, if you click update button here under full profile, you will be able to see the profile that got generated. So this basically telling that this is the charging discharging pattern that got generated. So during the summer months and all, battery charged more, discharged more. In the winter month, it had to do less. And now if you go back to the report here.
And also, Jakir, something to note as well, users can also switch to the battery system modeler. So if you go to the battery system modeler right now, right, under interval data, you'll see here, it's been automatically selected under the time series when you ran the battery profile creator. And now you can see the POI profile, but in addition to what the VPC is showing, you can see the 24-hour profile, the power histogram, right? So it gives you a picture of every day over a 24-hour period, what exactly is happening, when this battery system will be charging, when it will be discharging. The power histogram tells you, all right, the distribution of power set points on this planned battery system. And the energy histogram tells you the same for energy throughput as well.
Yep, good point. And then we're going to do the same here in the report, because report also gives us something similar information. So it first goes with application specific. So it is showing you that you are charging mostly during the daytime from the solar, and then you are discharging it back to the grid when there is a need. It gives you that 8760 profile for your batteries. And then it also showing you different analytics around what's going to be your net demand after adding the solar, adding the storage. So I'm going to skip this and jump to the main section here, which is the real question we have up until now is that we don't know that how big of a battery you're going to need. And this histogram is going to help us answer that. So what this histogram is telling us that on the secondary axis, this orange one is a cumulative distributed function. So if we pick a 17.5 megawatt battery, it's basically going to be able to meet the discharge requirement almost 98, 99% of the time, if you see it where it intercepts the y-axis. And to get to, so basically if we go at a 20 megawatt battery, we will be able to meet both charge and discharge side 100% of the time. So we can select a 20 megawatt battery from this, because we are trying to make sure we never cross that 90 megawatt threshold. Right? That's a hard limit from the interconnection perspective. So we are going for 100%. We want to make sure there is not a single point that goes up beyond that 90. So based on this, we decided, yeah, we need a 20 megawatt battery. And then we come to the energy histogram. This is telling us a similar story, that on the discharge side, we need maybe 55 megawatt hour. On the charge side, we need like up to 80 megawatt hour. So if we go with an 80 megawatt hour, we will be able to meet the energy requirements fully. So what we take out from this module here is that, yes, we're going to go with a 20 megawatt, 80 megawatt hour battery for this application. And then this is going to be the use case profile for that battery. With that, then we come to this battery system module. So you will see under general, as you switch, it's a 20 megawatt, 80 megawatt hour battery. We are not doing any augmentation at this for this example, just set it to user defined, set the usual parameters as we have discussed before. Interval data, so the power, this profile got automatically populated when we ran this other module, the battery profile creator, and then it gets loaded. Under equipment, this one we're using a 314 ampere hour model. Previous one we used 280, first one we used 306, now we're using 314, right? So we're using different battery models to see how the performance and things back. Inverters still kept the SMA1, and the enclosure still kept the same liquid cooled enclosure. Then you come here, you basically at this point click auto size, and this is gonna auto size the project for you. So if you click this, so primarily if you just do general, interval, and equipment, if you're not doing augmentation, those are the only three information you need. And then as soon as you input that, auto size becomes enabled. You click that, it's going to auto size the project for you.
So while that is running, something that's probably worth noting if we go back real quick to the energy histogram, Jakir, right? One of the uses of this energy histogram is to properly size your system. So in some scenarios, you would need to just double the energy capacity of your battery system to get that last 3% or 3 percentile of days on either discharge or charge, right? So it helps you identify when you start to get diminishing returns. Like for example, here on the charge side, if you look at the orange cumulative percentage, right? What seems to be going from, if you just look at from 30 megawatt hours to 40 megawatt hours, you're not really gaining much by going from 30 megawatt hours to 40 megawatt hours. So it helps the percentage of the days with certain charge and discharge throughput, so you can size your battery system based on a capacity that is not getting diminishing returns.
Right. Yeah, and then when the augmentation of the auto size finishes, it's basically showing you that your install capacity of 112 megawatt hour to get 80 megawatt hour throughout the project life POI. Okay. And you also need your inverter is a little bit oversized. You say we talked about doing 20 megawatt, but we need around 23.8 because of the losses and other factors that we talked about before. So once that's done, you basically at that point just go ahead and run it. And then into generate report. A couple of things are important here. So one thing we want to make sure that the system we design is able to meet the discharge power and energy requirement very well, because if we're not meeting our discharge commitment, then there is a chance that we are going to exceed the overall planned output is going to exceed 90 megawatt. So in this case, you can clearly see that on the discharge side, we are like 99.7%, and that's the goal, is to meet the discharge throughput. The throughput is a bit less because what the profile is trying to do is it is to put all the solar energy into the battery. So the battery is sized for discharge requirements. So you sometimes, like some scenario, like in certain conditions, you are not able to put all those solar energy back to into the battery because the battery is not big enough. And it doesn't need to be, because you only want to charge it enough so that you can meet your discharge requirement. All right, so with that, then you go ahead with the usual discussion, your RTEs, your losses. Another important thing for you to check is your overall POI capacity, which was 80 megawatt hour. This one, we didn't do any augmentation. So the initial system is completely overbuilt for 20 years. So we did that one. And then eventually you get the cost of your system along with all the operational cost and that we talked about. This one didn't have revenue. If you want, you could add revenue if you had a certain kind of contract structure, but we did this example without the revenue. So now, after doing all these, the main thing we're trying to look for, because our goal was to ensure that our overall plan output doesn't exceed that 90 megawatt threshold. So after you ran this module, the Storlytics output is that if you go to the generate CSV, it gives you exactly what the battery is going to be charging, discharging at the POI, right, at the battery point of interconnect. So if you go to the Excel, the output here, so if you output DSM, this is the one that just got created. There are quite a few different files that get created. There are some daily data analytics, annual analytics, and financial analytics. The one that we're looking for is this one, time step. So that's every time step, what happened in your system from all the way to point of interconnect to the battery terminal, losses and reactive power flows, everything is laid out here. So here, this is the column you're looking for. So this is what actually your battery is going to be doing. So if you take this one, P grid actual, and then combine that with your data center load and your solar production, then you will be able to get your net production. And that's what I have here. So here what it shows that the red one is the data center load, which was some places at times you can see over the years was going above 90 megawatt. But then the green one here is the data center net load after adding the storage and solar on top of it, right? So we can see that the green one never exceeds that 90 megawatt threshold. So what it basically tells us that with the help of solar and storage, we're able to add some flexibility and bring the interconnection limit from 100 megawatt to 90 megawatt. So in that way, now this data center is going to be able to connect with the utility without much of an upgrade requirements or delays. So I'm going to stop here. Obviously, there are a lot of other variations you can do. You might want to go back and add some diesel as well. It really depends on the shape of your data center load, as well as your solar, how big it is and how big of a footprint you have. But then if you want to add some other generating resource, you can come to the microgrid demand app through the wind profile. It says wind, doesn't have to be wind. So if you have a natural gas generator that is going to be running at a base load, you can input that through the profile here. So there are quite a few different resource mix you can do to determine what size of batteries you're going to really be needed to basically add data center flexibility. So that I'm going to stop here. Let's